In this video, we'll be dealing with Newton-Gregory interpolation. This question reads, Table 1 represents a cubic polynomial f of x. Use Newton-Gregory forward difference interpolation formula to determine the value of f of 0.5. Basically, Newton-Gregory forward interpolation is a numerical method used to estimate the value of a function at a given point based on a set of known data points. Let's proceed. We are going to input our data points in this table. Now the delta sign in this table represents our difference operator and is very useful in solving our interpolating polynomial. To find delta f, we are going to subtract our values of f, just as the name implies, the difference operator. Here we have -4 and we have -1. To subtract, we are going to say the final value minus the initial value. At this point, we are going to have -1 minus -4, and that is going to give us -1 plus 4, which is equal to 3. We are also going to apply the same thing here. We are going to find the difference between -1 and -2, and that is going to be -2 minus -1, which is equal to -1. We are also going to deploy that same method here. To find the difference between -2 and -1, we are going to say the final value minus the initial value, which is -1 minus -2, and that is going to give us -1 plus 2, which is equal to 1. We'll proceed. The final value minus the initial value, 8 minus -1, which is the same thing as 8 plus 1, which is equal to 9. 31 minus 8 is equal to 23. We will also apply the same method here. The final value minus the initial value, -1 minus 3 is -4. 1 minus -1 is 1 plus 1, which is equal to 2. 9 minus 1 is 8. 23 minus 9 is 14. Moving further, we are going to apply our difference operator by subtracting the final value minus the initial value. 2 minus -4 is 2 plus 4, which is equal to 6. 8 minus 2 is 6. The final value minus the initial value, 14 minus 8 is 6. Recall from the question, we have that table 1 represents a cubic polynomial f of x. This implies that since we are dealing with a cubic polynomial, the highest degree has to be degree 3. That is why we are stopping here. Now let's recall that our f of 0.5 is the same thing as f of x. This denotes that our x is the input, which further implies that 0.5 is equal to x. So we can conclude that our x is equal to 0.5. We are going to trace 0.5. We can see that 0.5 exists between 0 and 1. Between 0 and 1 would be 0.5 at this point. Now we are going to consider the boundary. The value on top will be denoted as our x0, while the value below will be denoted as our x1. So from the table, our x0 is equal to 0, our x is equal to 0.5, our x1 is equal to 1. We are going to find our point, x minus x0 all over x1 minus x0. So where our x1 minus x0 represents the constant range between successive values of x, which is often denoted as h. By substituting we are going to have our x, which is 0.5, minus x naught, which is 0, all over 1 minus x naught, which is 0, and this is equal to 0.5. Lastly, we are going to use this formula to find our interpolating polynomial. Our f of p will be equal to note this, I'm stopping at degree 3 because the question is a cubic polynomial. Now, how do we derive this formula? I'm going to use binomial series to derive this formula for easy understanding. Now, let's get the binomial series. So, recall from binomial series, we have that 1 plus x raised to the power of n is equal to 1 over 0 factorial x raised to the power of 0 plus n over 1 factorial x raised to the power of 1 plus n into n minus 1 all over 2 factorial x squared plus n into n minus 1 n minus 2 x cubed all over 3 factorial. But recall that 0 factorial is equal to 1. So therefore, we are going to have that 1 plus x to the power of n will be equal to 1 over 1, and x raised to the power of 0 is 1. So this is going to be 1 plus nx, because 1 factorial is 1 and x raised to the power of 1 is also x. So we're going to have plus nx plus n into n minus 1 all over 2 factorial x squared plus n into n minus 1 n minus 2 x cubed all over 3 factorial. Now, to represent this as our interpolating polynomial, our x would denote our difference operator. Here we are going to have that our x will become our difference operator and our n will become p. So this means wherever we see x, we are going to put delta, and wherever we see n, we are going to put p. So that is going to yield 1 plus delta raised to the power of p, which is equal to 1 plus p delta plus p into p minus 1 all over 2 factorial delta squared plus p into p minus 1 p minus 2 all over 3 factorial delta cube. Since it's a forward difference interpolation, it implies that f naught will be attached to our delta. Therefore, our interpolating polynomial, which is also f of p, will be equal to 1 plus p delta f naught plus p into p minus 1 delta squared f naught all over 2 factorial plus p into p minus 1 p minus 2 delta cube f naught all over 3 factorial. So this is our formula for our interpolating polynomial. And if you look at this, it is the same as the formula that was given earlier. But from the table, since we are dealing with forward difference interpolation, you can see that the number increase as we move downwards. So I'm going to draw a line which is going to move downwards. So from here, I'm going to have this. So we are going to consider these numbers just above our line. therefore we can say that our f of 0 is minus 1, operator f is minus 1, delta squared is 2, and delta cube is 6. So here we are going to say, but our f naught is equal to minus 1, delta f naught is equal to minus 1, delta squared is 2, and delta cube is 6. Recall that our p is equal to 0.5. So if we must substitute, we are going to have that our f of p will be equal to minus 1 plus 0.5 into minus 1 plus 0.5 into 0.5 minus 1 all over 2 factorial multiplied by 2 plus 0.5 into 0.5 minus 1 times 0.5 minus 2 multiplied by 6 all over 3 factorial. If we evaluate this, we are going to have that our f of p, our interpolating polynomial, will be equal to minus 1.375. Do well to like and subscribe to my channel. Thank you.